Hi guys, welcome back. In this video we will discuss visualizing functions of three variables. First we're going to review domains, of functions of n variables and what it means to have a graph of a function of n variables. And then we'll talk about how that translates to a function of three variables. So remember, let's say we've got a function of x1 through xn, and that's equal to w. Well, remember what we already talked about. The input is an ordered n-tuple. So f is taking some element from its domain, which is in n-dimensional space, and it's mapping it to a real number w. At least in this class, these are real numbers, n-tuples of real numbers, and this is a real number. So the domain of a function of n variables is always a subset of n-dimensional space, and then the output variable is always just a real number. So here are some specific cases. If we have f of xy equals z, well then the domain of this is going to be a subset of two-dimensional space. So we're going to find ordered pairs in the xy plane, and for each ordered pair we're going to assign it a z-value. So we're taking an xy in the xy plane and we're mapping it to z equals f of xy. Now when we do that, we get a surface. So here's my x-axis and there's my y-axis. And here's our z-axis. And that's supposed to be the surface z equals f of xy. Every point in the domain, so maybe this is our domain D. Every point xy in that domain, and this is in 3 dimensions, it's going to be x, y, and 0, is going to map to a specific point on the surface. And so we've got x, y, and f of xy. And f of xy is our z value. Now we've done this before. Let's go backward a little bit. Before Calc 3, Calc 1 and Calc 2, and in pre-calculus, our domain was just a single real number. So our domain was a subset of the real numbers, not a single real number. Not all the time. And then it mapped to another real number, and we called that real number y. So this function f would take a number x in the reals, and it would map it to y equals f of x, also in the reals. And notice that when I graph this function, the domain is just some interval over here, possibly the entire real line. And I've just drawn y equals x squared just to have an example. But its graph lives in two-dimensional space. So our input was a single real number, our output was a real number. So the graph of this function was a set of ordered pairs in R2. So it's a set of ordered pairs x and y, where y equals f of x in R2. So if I have a function of one variable, the graph lives in two-dimensional space, and we see this. I need one point for my input variable and one coordinate for my input variable and one coordinate for my output variable. Now over here, notice what happened. We're taking a bunch of points, or a bunch of ordered pairs xy in the xy plane, and we're mapping them to a z value. So the domain was a subset of two-dimensional space, that's down here, But when I graph it, I need a third dimension for that third variable, that z equals f of x, y. So the graph of a function of two variables consists of points x, y, and f of x, y. These are my independent variables. This is my dependent variable, because I'm thinking of z depending on x and y. But notice I need 3 coordinates. I need 2 for my domain elements, or not both of them together as a domain element, but I need 2 coordinates, 1 for each of my independent variables, and then I need 1 more for my dependent variable. So a graph of a function of 2 variables lives in 3-dimensional space. The graph of a function of 1 variable lives in 2-dimensional space. And in this video, we're talking about a function of 3 variables. So we're going to use w equals f of x, y, z. Now this is going to take x, y, z's from the domain of this function. So that's a subset of 3-dimensional space. And it's going to map it to a real number w. So we're associating with every x, y, z in the domain. We're associating that, or mapping that, to a w value in the range. Now, I can't graph this one. Notice that when I had a function of 1 variable, the graph was in 2-dimensional space. When I have a function of 2 variables, the graph is in 3-dimensional space, because I need 1 coordinate for each of my original variables, plus 1 more for that next variable, for that dependent variable that depends on all the other guys. So this function of 3 variables, its graph would have to live in 4-dimensional space. So the graph of w actually consists of a set of ordered, I guess, 4 tuples? Is that how you say it? You've got 4 variables now. I'm just going to call them a 4-tuple for lack of a better word. If you want, you can email me or talk to me after class about what that should really be called. But we're going to have x, y, and z, and then w equals f of x, y, z. So I've got 1 coordinate for each of my independent variables, and then I add 1 more for my dependent variable. Now this is going to be very hard to graph because we live in a 3D, we live in 3-dimensional space. We're comfortable, most of us are comfortable with 4-dimensional space-time, but we don't see the time variable when we look around. So we're going to have to do something different for this. We're not going to be able to draw it on a 2D piece of paper. But let's just write down the generalization. For a function of n variables, the domain of that function is a subset of n-dimensional space. But the graph of that function is a set of points in n+1 dimensional space. Because the graph of f consists of points x sub 1, x sub 2, x sub 3, all the way through x sub n. Those are our first n variables. And then the next one, the n+1th variable, is the dependent variable. It's that w, which is given by f of x sub 1 through x sub n. Now you might be saying to yourself, this seems a little silly. When on earth will we ever need more variables like this? It turns out it's very easy to think of examples. there are many functions that depend on more than one variable. Just for instance, let's say we're talking about temperature. I'm not sure if I did this in the other video already. I may have, and then it's just a review. Temperature we could think of as a function of x, y, z, and t. So maybe the temperature in some room depends on the 3 spatial coordinates. So we want to go so far in the x direction, so far in the y direction, and then up and down so far in the z direction. But then maybe the temperature also depends on time. Maybe that temperature is different at different times at that particular location. So this might be our function, or this might be our function, and the output temperature we might call W, just to have another letter to represent that variable. Now the graph of this, or excuse me, the domain of this is going to be a subset. Oops, I'll just write subset. That notation, it looks like a sideways U. That means that this is a subset of 1, 2, 3, 4-dimensional space. But the graph of t is going to consist of points like this: x, y, z, t, and then the temperature that goes with that particular x, y, z in time. So that W. Or if you prefer, you could say x, y, z, and t, and the temperature at x, y, z, and t. So this graph lives in 5-dimensional space because I've got 4 independent variables and 1 dependent variable. But there's no way I can visualize this. Even though this makes perfect sense, it's easy to understand. I can't draw this on a 2D piece of paper because I can't even draw the domain. The domain is a subset of 4-dimensional space. The graph itself lives in 5-dimensional space. We have no idea what that looks like. But I think one thing that I think is interesting is that the calculus that we study in this chapter works just as well, or almost all of the calculus that we study in this chapter works just as well for this function, this temperature, as a function of x, y, z, and t, as it does for more familiar functions that we can graph. We still might be interested in finding the maximum temperature. Like we might want to know, where is this maximized? What particular location and what particular time would allow us to maximize the temperature? And we might be interested in rates of change, like what happens to the temperature as x changes, as y changes, as z changes. What happens if we let 2 of them change and we hold the third and fourth constant? What happens if we let 3 of them change and hold the 4th constant? Like maybe we're wandering around 3-dimensional space and we're interested in this temperature at a particular time. Or maybe our space coordinates are all held constant and we're just interested in temperature or we want to see what happens to the temperature as time goes on at that particular location. So we could talk about the rates of change of this function. We could talk about where this is increasing as much as possible, which direction we should go in space and in time to increase our temperature as much as possible. We might want to find max temperature or min temperature at a particular location in time. All the math that we studied in Calculus 1 generalizes very nicely in multivariable calculus to a function like this, even though I can't graph it. Okay. So that was a big aside, and I'm going to write a note to myself. We're finally starting to talk about visualizing functions of 2 variables right here at 14:17. So I'll put that in the comments on this video. Now let's talk about what this video is supposed to be about. How do we visualize functions of 3 variables? We've talked about visualizing functions of 2 variables. We were able to graph a surface like this, and we were also able to infer what this surface might look like by graphing level curves. So we set z equal to a constant, then we had a function of x and y equals a constant, and we were able to graph those curves and imagine that those curves were elevated for different z values, and then by thinking of that set of level curves, the contour map, like a topographical map, we were able to infer what the function might look like in 3D. Okay, now let's think about this function. Let's focus right here. How do I visualize something like this? Well, if I want to visualize something like this, I'm kind of stuck because I still live in a 3D spatial world. Unfortunately, that's how things go for right now. All I can see is X, Y, and Z. And, you know, if we have a coordinate system and I've got an X-axis, a Y-axis, and then a Z-axis, and they're all mutually perpendicular, like these guys in our picture. If I draw any other vectors, they're all going to have if I draw any other vectors in three-dimensional space, they're all going to have components either in the X direction, Y direction, or Z direction. There's no fourth vector that I can draw that's perpendicular to all three of those at the same time. So that means I can't graph this. There is no fourth dimension to take care of this fourth variable over here. So I'm not able to graph this set of ordered 4 tuples in the traditional sense. But I can visualize this. One way that we can visualize functions of 3 variables is to think about like time-lapse photography. Time-lapse photography. If you've ever watched a video on YouTube of a flower growing, you see it like starting as a little seed and they've sped it up so that you can see the flower grow, that the spatial dimensions of that flower increase as time goes on. And so we see how this changes as time changes. Now, time only goes forward, but we're going to think of this W variable like time, except for that we can move it forward and backwards and think about what happens to the surfaces. Well, think about what happens to the resulting surfaces as W changes, much like we would when we're looking at a time-lapse photography of a flower growing or something like that. Okay, I think I may have butchered that. Let me say it more simply. I can't graph this in 4-dimensional space, but I can set W equal to a constant and graph the resulting surface in 3-dimensional space. We call those level surfaces. Okay, so that's what I was getting at. I can't graph W all at once, but I can graph level surfaces. So level surfaces are just surfaces that come from setting W equal to a constant and then graphing the resulting surface. If I have a collection of level surfaces for different values of W, that can give me some sense of how this function is behaving as W increases or decreases. We might want to know, well, what geometry do we have as this variable over here changes? And level surfaces can help us to figure that out. So here, let's do a simple example. I think this is probably the most popular example with graphing level surfaces. I have W equals a function of X, Y, and Z. And let's say it's equal to X squared plus Y squared plus Z squared. Now you might recognize that. You might be thinking off the top of your head that's the equation of a sphere, and you'd almost be right. This would be the equation of a sphere provided that W is equal to a constant. So spheres are going to be our level surfaces. Now we have to choose W whenever we graph level surfaces or level curves. You have to choose an output variable or an output number that is in the range of this function. So before we start graphing level surfaces, let's think about the domain and range of this function. Now if I want the domain of f Since it's a function of 3 variables, it's going to be a subset of 3-dimensional space. And remember what we said before, we can't divide by 0, we can't take even roots of negative numbers, and we can't take logarithms of negative numbers or 0. But there's no division here, so there's no danger of dividing by 0. There are no even roots, so there's no danger of taking the even root of a negative number. There's also no logarithms in the definition of my function. So it looks like we're good to go. Any x, y, and z I want, any real number x, real number y, real number z, if I plug those in, square them, and add them together, I'm going to get a w value out. So the domain turns out to be all of R3. There's nothing to write on the other side of that bar. It's everything. All of 3-dimensional space will work. Now be careful here. The range of this function is a subset of the real line. For every x, y, and z I plug in over here, I'm going to get a single w value. So I want to know, like, what kinds of w values do I get out from this? Well, remember, x squared is always positive except for when it's 0. So this is always non-negative. So the range of just x squared is 0 to infinity. If I let x get larger and larger, x squared gets larger and larger. The same is true for y squared, and the same is true for z squared. So the smallest that the sum of 3 squared terms could possibly be is 0. And I think if by choosing x, y, or z, or all 3 of them, larger and larger, the w values also get larger and larger. So the range of this function is 0 to infinity. I need to pick w values over here in this range. So I'm just going to start small, start with w equals 0. And then let's graph this also for w equals 1 and w equals 2. And maybe we'll go all the way up to, let's go all the way up to 4. Why not? Okay. So when w equals 0, I get 0 equals x squared plus y squared plus z squared. Now this is a particularly boring level surface. Not much going on here. There's x, there's y, there's z. Well, the only way this is going to be 0 is if x is 0, y is 0, and z is 0. So we get the ordered triple 0, 0, 0. So when w equals 0, we're right here at the origin. Pretty boring. Now let's see what happens when w equals 1. When w equals 1, I'm setting this, that's my w, equal to 1, and I have 1 equals x squared plus y squared plus z squared. And hopefully you say, ah, yes, that is the equation of a sphere centered at the origin with a radius of, well, r squared is 1, so r equals 1. So this is a sphere centered at the origin with radius 1. Remember, it's centered at the origin because we're not subtracting anything from the x, y, or z. And it's not, the radius isn't this number, it's actually the square root of this number. That number is r squared. R squared is 1, so r equals 1. So we've got a circle of or a sphere of radius 1 centered at the origin. So it's going to look roughly like this. Now we all know how hard it is to draw in 3D. So we just do the best we can. We say, that's my sphere of radius 1. So that's what w equals 1 looks like. W equals 0 is back here, w equals 1 was there. Now let's look at w equals 2. I bet you can see where this is going. I've got 2 equals x squared plus y squared plus z squared. That's another sphere centered at the origin, but now its radius is a little different. R squared is 2, so r equals square root of 2, which is approximately 1.4. So I'm going to go out. Here is x equals 2, y equals 2, z equals 2, but I don't want to go out to 2, I want to go out to 1.4. So we have a sphere centered at the origin, and we go 1.4 units out in every direction. And that's the surface that we get when w equals 2. Okay. Now let's see what happens when w equals 3. I bet you can guess it. We've got 3 equals x squared plus y squared plus z squared. So r squared equals 3. So r equals square root of 3, which is about 1.7. So I'm going to draw a sphere of radius 1.7. Okay, last one. The last one that's nice and easy to draw. We've got 4 equals x squared plus y squared plus z squared. That means r squared equals 4, so r is 2. So this is a sphere of radius 2, centered at the origin. It looks like I've just drawn a bunch of circles on top of each other. But the way you want to think about it is you want to think of this as a sphere that's changing. When w equals 0, we're right here. W equals 1, or as w goes between 0 and 1, we start from this single point at the origin, and that sphere starts to expand. It goes all the way out to 1. And then as w goes from 1 to 2, we don't get a sphere of radius 2, we get a sphere of radius square root of 2. And as w goes from 2 to 3, we don't get a sphere of radius 3, but we get a sphere of radius square root of 3. And then when w equals 4, we have a sphere of radius square root of 4, or 2. So in general, these level surfaces, I've got w equals x squared plus y squared plus z squared. So the radius of the sphere is w. If w is a constant, and we're just consider the constant w, I'm going to call that w naught just to remind us that that's constant. R squared is w naught, so the radius is the square root of w naught. So the level surfaces of this function of 3 variables are spheres centered at the origin with radius square root of w. And as w increases, those spheres start radiating out. So w goes from 0 to 1 pretty quickly, then from 1 to 2, and then 2 to 3, and then 3 to 4, and they just keep growing and growing like that. Okay, so that's one example of level surfaces. Now remember what we just did. First we had to think about the range of this function. Think about the range. Now the way we inferred this was thinking about perfect squares and how they behave. You frequently have to think about how squares behave. You also have to think about how square roots behave. Square roots are always positive except for when they're 0. That's typically going to give you the range. Things like that. Also, if I'm adding a bunch of positive things together, I only get positive answers except for when these are all 0. If these are all positive, the sum is positive. If they're all negative, the sum is going to be negative. Now, if this was a positive x squared and a negative y squared, well, as x increases, w increases. As y increases, w decreases. Like, things are going to change a little bit. So you might have a different range. But the first thing we needed to do was we needed to think about the range of this function. And then we picked w values in this range. And I like to pick w values that are evenly spaced so that I can have some sense of how fast w is changing. So w is going from 0 to 1. Like, look at that big gap, that gap from the origin out to that sphere of radius 1. That gap between w equals 0 and w equals 1 is so much larger than the gap between w equals 1 and w equals 2. So as W goes from 1 to 2, that sphere is, like, it's changing from 1 to 2, like over a very short distance. So notice that. And it's also changing from 2 to 3 over a very short distance, and then from 3 to 4 over a very short distance. So keeping these evenly spaced gives us some sense of how fast these surfaces are changing as W increases. Okay. So that was our first example. Let's do one more. Now this one looks a little bit ridiculous. I just made it up. So I've got W equals y minus the square root of x minus 2 squared plus z minus 3 squared minus 1. You might say, oh my goodness, Ms. Townsend, that is ridiculous. That's too much. So this is a function of 3 variables. And I've got something that looks like this. Okay. Now I want to think about range. Well, first of all, I know that whatever this is, whenever I'm starting to think about the domain, this expression under the radical has to be positive. So I'm going to take the square root of a number that's positive or possibly 0, and I'm going to get something positive or possibly 0 out. And I'm going to take a y value and I'm going to subtract this positive or possibly 0 number. So I've got a number over here minus a positive number. With that in mind, if y is large and positive, it could dominate. And as y gets larger and larger and larger, if this was 0, the w values would go to infinity. Now, if y was, say, 0, and the value under the square root got larger and larger, well, then we have 0 minus a large, negative number. So I think the range for this is all real numbers. And sometimes we abbreviate that this way, R and G of F equals the set of all W in the reals, and we said there were no restrictions on W, so it's going to be all real numbers. All right. So now I just want to pick some W values and see what happens, see what I get. Since it's all real numbers, I think I want to pick some negative ones and some positive ones and then see what changes, see what happens. So we'll try W equals -2, and then maybe W equals -1, W equals 0, W equals 1, and W equals 2. And then we'll see what these surfaces look like. Okay, so let's see what W equals -2 looks like. So I have -2 equals y minus the square root of x minus 2 squared plus z minus 3 squared minus 1. Now it looks a little bit ridiculous, but the reason for that is I wanted it to be a level surface of something that, or a surface that we were familiar with from an earlier chapter. And I didn't want that center to be at the origin, so I did this thing with the -2 and the -3. So that's why it looks a little weird. But let's rearrange this equation until it looks like something we're familiar with. So let's subtract the y from both sides. So I have -y minus 2 equals this negative square root. And let's multiply both sides by -1 to get rid of the negatives. And let's square both sides to get rid of the square root. So now I've got y plus 2 squared equals x minus 2 squared plus z minus 3 squared minus 1. And if I move that 1 to the other side and move this y plus 2 squared to this side, I've got 1 equals x minus 2 squared plus z minus 3 squared minus y minus 2 squared. And we're used to putting them in alphabetical order, so let's write it this way instead. You see what it is? Do you notice that that is, well, I've got 3 squares, 2 positive, 1 negative, and a 1 over here. So this is a hyperboloid of 1 sheet. It opens parallel to the y-axis because the y is negative. And I don't believe there are any restrictions on x, y, or z. Well, we ended up with y plus 2 had to be that positive square root. So y plus 2 must be positive. I guess that's a restriction. Has to be greater than or equal to 0. So y has to be greater than or equal to negative 2. Okay, so what does this hyperboloid of 1 sheet look like if y is greater than or equal to negative 2? This is kind of a weird one. It's because I made it up. That's okay. Sometimes you get weird surfaces. Okay. First, notice what our center is. It's x equals 2, y equals negative 2, z equals 3. So go to negative 2 for y, positive 2 for x, 3 for z. I'm just going to plot my point. 2, negative 2, 3. That's right here. And normally I would just draw a hyperboloid of 1 sheet that opened in the y direction. So it's going to open like left and right like this. But we only want y greater than or equal to negative 2. So it's a little strange. We're going to see something that looks roughly like this. The rest of the hyperboloid of 1 sheet that would have been over here, it's not part of the graph. We're only interested in that one, this side. And that is when w equals negative 2. That's what we get. It is odd. It's because I made it up. Sorry, guys. Okay, now let's see what happens if we let w equal negative 1 instead. Well, I think pretty much everything's going to stay the same. We subtract the y from both sides. Multiply both sides by negative 1. So then this time we've got y plus 1 has to be positive, or possibly 0, because we're taking a positive square root over here. So y has to be greater than negative 1. Greater than or equal to negative 1. And then when we square both sides, we get this. So I have 1 equals x minus 2 squared minus the quantity y plus 1 squared plus z minus 3 squared. And that is another hyperboloid of 1 sheet opening parallel to the y-axis. But the center is different this time. The center is 2, negative 1, 3. Remember, we take the opposite of those numbers. The center of this one was 2, negative 2, 3. So that was our center before. So our center was 2, negative 2, 3 when W was equal to negative 2. Now it looks like over here we have a center of 2, negative 1, 3 when W equals negative 1. See a pattern? Okay, so that's y equals negative 1. So I'm drawing my rectangular box. It's a little bit hard to see because this box is inside the other box. And this is the point in the center for the new one, the new hyperboloid of one sheet. So I end up with something that looks like this. That's what our surface looks like when W equals negative 1. You see a pattern? The center moved 1 unit down the y-axis. Okay. All right, let's look at what happens when W equals 0. So I've got 0 equals y minus this quantity subtract the y from both sides, multiply both sides by negative 1. Now I've got y equals a positive square root, so y must be greater than or equal to 0 this time. 0, not negative 1. And when we square both sides, we get this. Rearrange your equation, and you get this. It's another hyperboloid of one sheet. The center has moved again. The center is at 2, 0, 3 this time. Notice it's at 2, 0, 3 when W equals 0. I think that center is moving. The center was, I didn't write it down for the first one. The center for the first one was 2, negative 2, 3. The center for the next one, that was when W was equal to negative 2. So it was 2, negative 2, 3 when W was negative 2. So the y coordinate of the center was negative 2 when W was negative 2. Then when W was negative 1, the center was here. The y coordinate of the center is also negative 1. When W was 0, the y coordinate of the center is 0. I think what's happening is that as W changes, we're changing that y coordinate of the center. And we're also moving this value where it's defined. It looks like this is always defined for y greater than negative 2, negative 1, 0. So it's going to be defined for y greater than, well, this negative 2, negative 1, and 0 is the W values for y greater than W. So this one, let's sketch it in a different color. It passes through this point. That is 2, 0, 3. Otherwise it has exactly the same shape as the others. It's just moved down a little bit. Let's just do one more to be sure. I'm pretty sure when W equals 1, the center is just going to change to 2, 1, 3. But let's check it out and be sure. So we've got 1 equals y minus the square root. Subtract the y from both sides. And then multiply both sides by negative 1 to get rid of that negative right there. So we've got. So now y minus 1 needs to be positive, or possibly 0. So y has to be greater than or equal to 1. Good. It's exactly what we expect with our pattern that we're seeing here. And then we square both sides. Add the 1 to this side, subtract that guy from that side. And we've got a hyperboloid of one sheet with its center at 2, 1, 3. Hey, that's exactly what I expected. The y coordinate of my center is changing. The x and the z are still centered at 2 and 3, or the x naught and z naught are still 2 and 3. But we've got our hyperboloid of one sheet, and it's just moved 1 unit basically to the left. Whenever we're looking at it from this direction, it looks like it's moving to the right relative to us. So when, let's go back to purple. When w equals 1, we go here. X equals 2, y equals 1, z equals 3. So I'm going to draw my rectangular box. There's my new center. I'm going to draw the same shape as before, but again, it's exactly the same shape. Look at these equations. The only difference between this one, let me highlight it in some way. Let's look at that equation, and that equation, and this equation, and this equation. They are identical, guys, except for one little thing, one little very important thing that changes from surface to surface. The only difference between this and this is that minus, or that plus 2 and that plus 1. And the only difference between this and this is that there's a plus 1 there and there's nothing there. On this one, we have a minus 1. So these shapes, they're exactly the same shape, but we are adding or subtracting something new from the y every time. As w increases, this value that we're adding to the y decreases, actually. Or alternatively, we can think of it this way. The w value is going to be the y coordinate of our center. The x coordinate of our center of our hyperboloid of one sheet is 2, and the z coordinate is 3. But that w value is giving me that y coordinate. So as w increases, I've got half of a hyperboloid of one sheet, and it's moving down in the y direction. Okay, so that is how we visualize functions of 3 variables. We're imagining these as surfaces that change as w changes. So as w changes for this one, we had a surface, a half of a hyperboloid of one sheet, moving down the line, the line that's right here that's parallel to the y-axis. X equals 2, z equals 3, and y is just increasing the whole time. It's moving down that line. So there's a center line here. And it's just that it's moving down that line as w increases. Now in our other example, our spheres changed size. As w increased over here, I went from a single point in 3-dimensional space to a sphere of radius 1, and a sphere of radius square root of 2, and a sphere of radius square root of 3, and then a sphere of radius square root of 4, which was 2. And so as w increased, our spheres got larger and larger. On this one, we just have a translation. It's just going farther and farther to the left relative to the origin. If you're standing at the origin, it's going to look like it's moving to the left. From where we're standing, it looks like it's moving to the right. But it's moving in the positive y direction. As w increases, y increases, and this little part of the surface that we're interested in, or that level surface of our function of 3 variables, it's just translating to the right without changing its shape. Okay, so that's it for visualizing functions of several variables.